You clicked on this video because you saw deep SWE benchmarks promising cheaper AI development costs for your projects. You are worried that the industry hype about falling prices might be misleading when it comes to your actual budget. The real problem is that these per-task cost metrics hide massive operational overheads, meaning a task listed as 5 cents can actually cost you $2.50 in production. By the end of this video, you will understand exactly why those benchmark numbers fail so spectacularly at scale and how to avoid underestimating your infrastructure costs by orders of magnitude. Let us start with what is happening right now in artificial intelligence evaluation. Recent analysis of the SWE-bench verified dataset suggests that inference costs are dropping dramatically every single year. The data claims we should see a 5 times to 10-fold annual drop in spending just based on current benchmarks. This sounds like fantastic news for any junior engineer looking to build complex agents without breaking their bank account. It implies that algorithmic improvements and hardware gains are making intelligence cheaper at an accelerating rate. But here's the thing. This narrative creates what researchers call a deep SWE trap. The trap exists because these metrics measure price efficiency in isolation while ignoring the rising operational reality of running frontier models today. The core issue lies in how we define cost per task. When you look at a standard benchmark result, it usually records the successful completion of a single software engineering problem as one unit. If that task takes 3 minutes and uses 2,000 tokens, the system calculates a tiny price tag for that success. This calculation assumes everything goes perfectly the first time every time. It ignores the messy reality of production systems where failures happen constantly. In real-world deployment, an agent often fails to solve a problem on its initial attempt because it misreads code or gets stuck in a logic loop. Each failure requires a retry, and each retry consumes more tokens and burns through your budget without adding any value. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider the difference between theory and practice here. A benchmark might show that a single task costs 5 cents when everything worked perfectly. But if you factor in the necessary failure-retry loops required to handle complex codebases, that same operation can easily cost $25 or more per successful resolution. The metric hides this explosion because it only counts the final success state and discards all the intermediate failures from its calculation. This means a theoretically cheap task becomes an expensive production operation once you add the reality of iterative agent behaviors. You are paying for every single attempt, not just the one that succeeded. There is another layer to this problem involving context loading and token limits. As models grow larger and more capable, they require massive amounts of memory to hold entire codebases in their working context at any given time. This creates a phenomenon known as context-bloat, where successful task completion requires retaining huge files in memory just to understand the environment. The cost per effective token becomes nearly infinite for complex multi-file engineering problems, because you are paying to store and process vast amounts of irrelevant data alongside the actual solution logic. Benchmarks that treat LLMs as deterministic oracles fail to account for this overhead, leading to estimates that are wildly inaccurate when scaling beyond single-task success rates. This leads us into what experts call the plausibility trap. This occurs when developers apply probabilistic engines to tasks that require deterministic verification steps. In software engineering, you often need to check if a file exists or verify syntax correctness with absolute certainty. These are binary questions that do not benefit from the heavy lifting of large language models designed for creative reasoning. Yet many automated workflows treat every step as a complex inference problem. The result is a 6.5 times latency penalty when these engines are misapplied to simple verification tasks. You end up paying for expensive probabilistic reasoning on steps that should be handled by deterministic logic, inflating the true cost of software engineering tasks significantly. We must also look at the economic forces driving model bloat alongside algorithmic efficiency gains. While data confirms that pure algorithmic efficiency improves at a rate of 3 times per year, this progress is often negated in practice by other factors. The actual cost of running frontier models has risen between 3 times and 18 times annually due to larger context windows and increased reasoning demands. This creates a conflicting dynamic where the raw price per token might drop slightly, but the volume of tokens required skyrockets because problems are becoming more complex. Developers who adopt these benchmarks for production budgeting ignore this efficiency tax entirely, leading to architectural decisions that prioritize model size over the algorithmic efficiency needed for cost-effective scaling. The gap in current research is significant regarding how we quantify failure loops and context-switching penalties. Most evaluations isolate single-task success without measuring the cumulative cost of iterative agent failures or the time spent reloading massive contexts between different parts of a codebase. Without accounting for these hidden operational taxes, developers risk underestimating production costs by orders of magnitude when they move from testing to deployment. You cannot simply multiply your benchmark score by your user base and expect it to match reality because every interaction introduces new failure modes that the benchmarks never recorded. The solution requires a shift in how we evaluate AI agents for engineering workloads. Instead of focusing solely on per-task success rates, you must measure the total cost including all retries, context loading times, and verification steps performed by probabilistic engines where they are unnecessary. This means designing systems with deterministic fallbacks for simple checks rather than relying on heavy models to do everything. It also requires building monitoring that tracks every single token consumed during a failure loop so you can see exactly where the money is going. Only then will your cost estimates align with what it actually takes to run these systems in production environments at scale. The data from recent studies shows us clearly that price efficiency driven by hardware alone cannot overcome the rising complexity of modern AI applications if we do not change our evaluation metrics. The DeepSWE Trap and Plausibility Trap are real dangers for anyone trying to build reliable, affordable software agents today. If you ignore these hidden costs now, your production budget will explode when you try to scale beyond a few hundred successful tasks per month. You need to account for the non-linear overhead of context loading and token limits before it is too late to adjust your architecture. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.